So we have previously looked at how you can compute the output of a linear and time invariant system or a filter if you're given the input x of n and the filter's impulse response h of n. So for today's lecture we will shift the focus slightly and look instead at how you can design the filter itself, so how you can choose the impulse response such that the filter has some predefined characteristics and thus something that you wish it to do. And typically we'll define what we want the filter to do in the frequency domain by specifying the frequency transfer characteristics that we wish the filter to have. In order to motivate why filter design is an interesting problem, it's illustrative to consider the case of the ideal low-pass filter. So if we just look at frequencies in the range -1/2 to 1/2, the ideal low-pass filter is a filter such that its frequency response is equal to 1 for every frequency up to a cutoff frequency nu c, and then 0 immediately after. So what the ideal low-pass filter would do is to an input signal would be to keep all frequencies up to the cutoff frequency unchanged and remove all other frequencies. So if you take the inverse discrete time Fourier transform of the frequency response, we would get the impulse response, which would be given by this expression, which is better known as the sinc function. And if we look at this in a particular case, so in this case with a cutoff frequency of 1/6, the impulse response would look like this. So what we see in this impulse response is that it extends infinitely ahead in time and infinitely back in time. So this property that it extends infinitely back in time implies that we couldn't implement this filter in general, because if we were to implement this filter we would need to know the input signal infinitely ahead of time in order to be able to multiply with these taps of the filter. So since we cannot implement an ideal low-pass filter exactly, the topic of filter design would be to come up with an implementable filter design that could in some sense approximate this ideal response up to some degree of accuracy. And this is what the topic of today's lecture will be about. In order to have a well-defined design problem, we would need a specification of what type of properties we would require from the filter that we design. So if we consider the specific case of the low-pass filter, it could look something like this picture. So since we cannot build an ideal low-pass filter, instead of saying that we wish the filter to be identically equal to 1 for the so-called passband, we would say that it needs to be within a range of 1 minus delta p to 1 plus delta p, where delta p is some parameter that specify how close to the ideal response should our filter be. Similarly, in the stop band where the ideal filter would be equal to 0, we say that our filter design needs to be less than some delta s value, which would be chosen close to 0 in order to have a good approximation of the ideal response. And we would also need to allow for some transition band where the filter response is allowed to drop from the levels of the pass band to the levels of the stop band. So with such a given design specification, a particular solution would then be an impulse response which satisfies these design criteria. So for instance, this frequency response. And obviously this would have to be the frequency response of an implementable filter in order for the design to be usable. Generally speaking, the set of filters that we could implement are the filters that have rational transfer functions, meaning that the C transform of the impulse response h of z, or the transfer function of the filter, has the following form, being the ratio of two polynomials in C, and where n here is a fixed integer typically referred to as the order of the filter. So this set of filter would also include these FIR filters that we looked at before when doing the filtering with FFT in the frequency domain. So, but in the general case, since these filters will have an infinite impulse response, you couldn't implement them by simply convolving the impulse response with the input, but you could implement them in this recursive structure that I'm sure that you've seen before. So the way that you would implement them would not be to convolve directly with the impulse response, but instead you would take the input signal x of n, feed it into this circuit which creates several delayed copies of the signal, which are then fed back into itself through these feedback links and multiplied by these coefficients a1 to an, and with the output multiplied by the coefficients b0 to bn in order to create the output signal y of n. So using this circuit we could create the equivalent of doing this infinite convolution with the impulse response, but only spending 2n multiplications per output sample in y of n, and this would be the way to implement the filter. The way to design the filter would typically be done by placing zeros and poles of the transfer function in some logical way. And you can do that directly, or you could rely on classical methods of placing zeros and poles. And I'm sure you have seen this before as well. So there would be the Butterworth and Chebyshev designs, which are standardized ways to place the zeros and poles of the transfer function. But you could also rely on tools like the bilinear transform, which is a tool that allows you to take analog filter and turn it into an equivalent digital filter by mapping the frequencies of the discrete Fourier, or the time continuous Fourier transform to those of the discrete time Fourier transform. But we will not look explicitly more at IIR filter design within the course, but instead focus on the case of FIR filter design. FIR filters can also be implemented in terms of a circuit, and we could obtain this circuit from the IIR case by setting all of the feedback coefficients equal to 0, removing the feedback part of the IIR circuit. So this would lead to a filter that has a finite impulse response, and in particular it would have an impulse response of length equal to the order of the filter plus 1, and the impulse response of the system would be directly given by these B coefficients in this case. So taking an input signal x of n, feeding it into this circuit and obtaining y of n at the output would be equivalent to convolving the input signal with this impulse response. But as we've seen before in the previous lecture, this is not the only way to implement an FIR filter, but we could also implement it in the frequency domain, which could be more computationally efficient, especially when the order or the length of the filter is quite large. There are also several different ways that are particular to FIR filters in terms of the design, and we'll look at some of these in the course. So we'll look at a technique called frequency sampling, where you essentially specify the frequency response you want for the filter at specific chosen frequencies. We'll also look at the window method, which instead works by taking an ideal filter design and trying to remove samples from the infinite impulse response in order to build a finite impulse response with some controlled properties. But you can also think about optimization-based methods, and there are several of these, where you could essentially ask questions like, what is the minimum order filter that satisfies a given set of constraints in terms of the transfer function? Or if we specify the order of the filter, we could ask for a filter that has a certain ripple in the pass band, but as low ripple as possible in the stop band, for instance. But these filter design methods typically require mathematical tools that will not be required for this course, so we'll skip the optimization-based methods and concentrate on the window-based methods and the frequency sampling method. The main benefit of an IIR filter design is that you can create sharp transitions in the frequency response for relatively low values of this capital N, or the order of the filter, meaning that with a relatively low complexity you can create a filter that transitions quickly from the pass band to the stop band. But there are several different properties of the FIR filters which are also beneficial for their choice. So for instance, for any set of these coefficients B0 to Bn, the filter will always be stable, since we don't have this feedback part which could potentially make an IIR filter unstable if the A coefficients are chosen incorrectly. Also, even though we may have to choose n quite large in order to satisfy the design parameters, we know that we can use the FFT algorithm to implement the filter quite efficiently in the frequency domain instead. And being able to choose n large also increases the degree of freedoms we have in the design, so we can ask several other things to be satisfied by the filter. A third property is that with a linear or an FIR filter, it's easy to ensure something called linear phase. And we'll discuss this in more detail for the remainder of this video before concluding. So if we look at the case of the ideal low-pass filter again, where we had an impulse response being given by this sinc function, we could introduce a time delay into the sinc function, which would correspond to a shift in time. So if we introduce a time delay of capital M samples, the effect this would have on the transfer function of the frequency response would be by the multiplication of a complex scalar e to the minus j2 pi m nu, where nu is the normalized frequency. So this would still be an ideal low-pass filter in the sense that the filter has unit gain in the passband and zero gain otherwise. So the plot of the absolute value of the transfer function would look exactly the same as before. However, this phase shift here is what corresponds to the shift in time, so it would correspond to a shifted version of the impulse response. And if you look at this phase, it has this particular property, namely that it grows linearly with this normalized frequency. And this is what the linear phase is all about, as linear phases correspond to pure time shifts of the impulse responses or output signals. So let's exemplify that with an example. So again, we have this time-shifted version of the ideal low-pass filter. And we take an input signal x of n, which is consists of two additive components, x1 of n and x2 of n, which have Fourier transform of discrete time Fourier transforms x1 of n and x2 of n. And we assume that x1 of n, the Fourier transform for the first component, is such that it doesn't have any energy in frequencies outside of this cutoff frequency of the filter. Likewise, we'll assume that the second component, x2, has a Fourier transform which is 0 within this range between minus νc to νc. So it only has energy outside of the range identified by the cutoff frequency. So if we have such a setup with this input signal x of n, what would then be the output if we take this input signal and convolve it with the impulse response of the system? In theory, of course, because we cannot do this in practice. So will it be equal to the input signal? Will the output be equal to a time-shifted version of the complete input signal? Will the output be a time-shifted version of the x1 component, or will the output be a time-shifted version of the x2 component? The correct option is option number 3. There will be a time-shifted version of the first component. The reason for this being that the second component is completely removed by the filter, since it only has frequencies outside of the range let through by the filter, and the input signal x1 will remain unchanged up to this shift by this scalar, which corresponds to the time shift that we see in the signal. We can exemplify this further by considering the case of a sinusoidal input signal. So let's assume that the input signal x of n is a sinus signal with amplitude a, frequency or normalized frequency μ0, and phase theta. Then we know that if you have a frequency response and you split it into the magnitude of the frequency response and the phase of the frequency response, the effect this will have on the sinus signal at the input will be to give an output signal which is also a sinusoid with exactly the same frequency, but the amplitude has been changed by the absolute value of the frequency response at the particular frequency of this sinusoid, and there will be a change in phase equal to the phase of the frequency response at this particular frequency. So we can now introduce a quantity usually called the group delay or the envelope delay, denoted tau, which is the derivative of the phase of the frequency transfer function with respect to the frequency, and then normalized by 1 over 2 pi and with the minus sign. And let's look at that in a particular example. So let's look at the case where we don't have just a general frequency response, but we have a frequency response where the phase grows linearly in this fashion with the normalized frequency, and see what this amounts to. So we still have an input signal, which is this sinusoidal signal like before, and we can write the output signal as we saw with an amplitude changed by the absolute value, but we could incorporate this change in the phase into the time variable here. So the output would be simply a scaled version of a time-shifted copy of the input signal, where the time shift would be exactly this value m, which appears here in the phase. And if you work out what the group or envelope delay is for this particular phase, you would find that it's an integer equal to this m, which is the time shift that appears here. So what we could say is that for a constant group delay, so if we have a filter with a constant group delay, meaning that it has a linear phase, so a linear phase, if you take the differential of that, you would get a constant. So if we have a constant group delay, that corresponds to a delay of the input signal, but we still have this change in amplitude. And we can exemplify that in a particular case where we try to low-pass filter an image. So here we have an image of some peppers. We have a filter which has amplitude of the frequency response as shown here. So it's a low-pass filter. It's not an ideal low-pass filter, but it will tend to let through low-frequency components more than it will high-frequency components. And here we plotted the phase of this filter. So as you can see, it's a linear phase. You have these jumps in the phase, but that's just here because the fact that I've mapped it to the range minus 180 degrees to 180 degrees. And of course there is an ambiguity there in the phase, so if you add more than 180 degrees you come back to where you began. And you can also have these rapid transitions when the filter response is identically equal to 0 because the phase is not well defined at this point. But still, if you look at this and what the filter does to the picture, you see that what you get is a smoothed version of the picture, which is consistent with this low-pass filtering ID. You will also see that the filter or the image has shifted slightly to the right and down because I filtered in both the X and Y direction. And this particular shift is exactly 4 pixels in this case, which corresponds to the derivative of the phase of the filter, which is this group delay. So the group delay for this particular case is 4. And look now at what happens if we change this example to, instead of considering an FIR filter which has this linear phase, we instead consider an IIR filter which has a non-linear phase. So the amplitude of the filter of the frequency response remains exactly the same as before, but the only change now is that we have a filter whose phase is not equal to a linear phase. And what we can see here is that this completely destroys the picture, the filtered pictures. And the reason for that is that different frequency components, so low frequencies and higher frequencies, are shifted by unequal amounts, and this is what causes this ghosting effect here. So what we can conclude from this is that if you filter images, having a linear phase so that each frequency component is time delayed or shifted in this case by an equal amount is extremely important. And you can also ask now what type of properties an FIR filter H of n needs to have in order to have a constant group delay. So what type of properties should we satisfy in the design process in order to create the filter with a frequency response that is given by a real valued function of the frequency times some complex exponential that is linear in terms of the frequency and has this group delay in the exponent. It turns out that this can only be satisfied if you satisfy a certain symmetry property in the time domain. So in particular, the FIR filter's impulse response should be equal to itself in a time reversed manner times either 1 or minus 1. And it turns out that the group delay has to be equal to exactly the number of taps in the filter, or the order plus 1, over 2. So the group delay should be the number of taps divided by 2. And this creates essentially 4 different classes of FIR filters which has this constant group delay or has the linear phase property. So either k is 0 or 1, or m is even or odd, or the order is even and odd. And we can plot these different cases here. For the case when the filter order is even, k is equal to 0, we would have a type 1 filter. We would have a so-called type 2 filter if the order is odd, so the number of samples are even, and k is equal to 0. So these are the 2 symmetric designs. But we could also have 2 antisymmetric designs. One for when the order is even, so when the number of taps is odd, and an antisymmetric design when the number of taps is even or the order is odd, and k is equal to 1 in both of these cases, meaning that the first part of the filter is equal to a negative version of the second part of the filter time reversed. It turns out that these types of different FIR filters with the linear phase have some added properties inherent in the design which makes them more or less suitable for implementing different kinds of filters. So look at a question here where we have 4 statements. The first statement being that a high-pass filter can be of type 1. Second statement is that a high-pass filter can be of type 2. Third statement that a low-pass filter can be of type 3, and a fourth statement that a low-pass filter can be of type 4. It turns out that only one of these statements is correct. So can you see which one? Well, the correct answer is option number 1. A high-pass filter can be of type 1. So in order to see why this is the only correct answer, we can try to eliminate all of the rest of the options. So for option 3 and 4, we see that if we sum over the components in either a type 3 or a type 4 filter, that sum will run to 0, which means that the DC gain of both type 3 filters and type 4 filters will by design always be equal to 0, meaning that they will always remove the DC signal, and that's not very good for implementing a low-pass filter. Similarly, if we look at number 2 as a high-pass filter and send in the most high frequency signal that we can think of, so signal which changes between -1 and 1 between each sample, you can see that the convolution of such a signal with such a symmetric filter will always lead to 1. So a type 2 filter will always hinder the highest frequency component. So implementing a high pass filter in type 2 is not a good idea. However, type 1 filters can implement any kind of filters like low pass, high pass, band pass and band stop filters, which is why you often see designs based on type 1, because this is the most general case. So to summarize this first video on filter design. So what we've seen so far is that ideal filters are not realizable, but we can approximate them using realizable structures such as the IIR filters that can be implemented using the circuit containing the feedback structure. Or we could implement or approximate ideal filters using FIR filters that can be implemented either using a circuit or implemented using methods like overlap save and overlap add that rely on the FFT algorithm for efficient computation. We've also seen that FIR filters that satisfy certain symmetry or antisymmetry properties will be guaranteed to have linear phase. So linear phase is a property that is sometimes very important and sometimes not. So if you're working, for instance, with an audio application, it turns out that we are relatively insensitive to phase differences when we listen to signal. However, if we view a signal, as in the case of an image, we're extremely sensitive to changes in the phase. So for applications like image processing, having a linear phase is absolutely crucial. And then it's good to know that we can satisfy this property in FIR filter designs.